We already observed that our instructions can be roughly broken up into the following steps. Instruction fetch, pen, instruction decode and register. Fetch in the third step branch and jump instruction can be complete for the other type of instruction. We can perform the memory outputs, computation and execution part in the fourth step or type in instruction can be complete. And also we can complete the store warden instruction or for the load word. In this step we can access the memory, and in the fifth step the memory read instruction can be complete. So all of the instructions take 3 to 5 steps to complete, and the first 2 steps are performed identically in all instructions. Let's define each of these steps in instruction for each step. The memory that indicates by program counters should be read and its value should be stored in instruction register. And also the program counters should be incremented by 4. So for this purpose, the content of the program counter should be sent to memory, and the written instruction from the memory should be stored into the instruction register, and the program counter should be incremented by 4. The highlight hat in this data part is corresponding to this operation. Let's check it together. The program counter value will be used as the address value of the memory. The result or retrieved data from the memory will be stored in an instruction register. Also, the program counter should be incremented by 4. Also here, or a new source should be 0 and all new source B should be 1 because we want to select a constant for an program counter. And here you will compute the program counter plus 4 and it comes here. Then from the PC source control we have to select 0 and this value will be come back and we write on the program counter. So these are the values of the control signal. As you can see, program control should be 1 memory. Read should be 1. This is a memory. We signal memory, write should be 0 because we don't want to write anything in the memory. The instruction write control should be 1 because we want to save this data in the instruction memory. Only the instruction register has a control signal at the other registers. Always. If we write the data in the input in the memory inside them, recycle every clock pulse they all use. Source A should be 0. As I mentioned, I'll use source B should be 0, 1. Second input should be select or new operation should be 0, 0. This is a question we want to perform. Addition or a new operation is 0, 0 and register write also should be 0. We don't want to write anything back into this register. So these are all of the control signal for the first step or instruction fetch. The next step is an instruction. The code and register fetches step. So in this step we use instruction register content to read to value from the register file. So tweet 2118.25 will be used and we read the data from the register file and save it in the register A, and this fields will be used to read the second operand from the register file and it will be stored in the register B. Meanwhile, we want also to perform this operation. The program counter will be added by sign extended of 16 lists, significant piece of the instruction register. And this value also should be shifted 2 times to the left. We don't know which one of these 2 parts are necessary, so we have to perform both of them. If the instruction is registered instruction or are typed in instruction, we need this part. If it is a load, word, or branch equal or so, we need this part. So please are the control signal in the second step or second stage to the value operator should be 0, 0 for the operator. Again, we want to perform addition. We can see the instruction bits from 21 to 25 and 16 to 20 will be used to read to data from the register file, and they will be stored in A and B. Here, the program counter. And from this part, the sign extended and shift to time to the left value of the immediate value should become, and they will be add to each other. So the value operator should be add this to value. And this value will be stored in the value output. This is the register to temporarily store the result of the value for the next stage execution step. Here is where our instructions diverge. For memory reference, the value out is equal to the register, a plus sign extended of the 16 least significant part of the instruction register for arithmetical and logical instructions. The value out contents value of the AOPB, the operation that defines by function. Part of the instruction is performed over the content of the register A and B, and it is inside a value out in the branch instruction. We want to check that if the A and B registers are equal, then the program counter should be lowered by the value that is stored in OIL U out register and in the jump in instruction. We want to concatenate the 4 bits of the program counter, the higher 4 bit of the program pointer, with the 26 bits of the instruction register, which are shifted 2 times to the left. Let's see each of these different instruction types. Execution part for memory reference should find the address of the current. So the 16-bit on the instruction memory extended to 32 bits, and this 32-bit address will be add with the register by using the value. And then this value should be used as the address memory or in the next step. So all your oppression is again 0, 0. Because we want to add this to numbers. I'll use source A should be 1 because we want to get this a register, and I'll use source B should be 0, 1, 1, 0, or number 2 in order to select this sign extended immediate value. And the result will be a store in the value out register. For the arithmetical and logical operation, as you can see, the value of the register A and B will be given to the OIL U. So the OIL U source A should be 1 and OIL U source B should be 0, 0 to select this one, and the result will be a store in the OIL output register. Also, as you know, the function part of the instruction is the first 6 split in the right side. So we use this part as the input of the OIL U control. So OIL U will be applied the function that defined by the instruction over this to A and B value. It can be add, subtract, and X or other type of operations that can be performed by value, and they are determined by the function field. After instruction they beat 0 till 5. For the branch instruction, first, we have to compare the value of the 2 operand. The operands are inside register, and B we give them to the value. So this multiple Excel or source H should be select 1 and source B should select 0, or the source B should be 0, 0 and source A should be 1. The all you should subtract these 2 values. So as you can see, all the operation is 0, 1. Then this 0 or 0 result should be used and it will be. And with the program write control, if both of them are 1, then the program counter will be loaded with the value that is stored inside the value out. So these multiple Excel or PC source should select 1. So as you can see, the source is 0, 1. So the branch address which is stored in the value out in the previous step, will be loaded and come back here to the program counter. Finally, for the jump in instruction, the execution step is we use 26 feet of the instructions here. And this 26 between instructions shift 2 times to the left, it becomes 28-bit. Now also it's concatenate here by 4 bits of the program counter. Now it's become 32 bits. This 32 bits target should be loaded into the program content for jumping instruction. So in the jump in instruction, the PC source should be 10. We want to select input 2, so it should be 10. And the PC write again is another control signal. Right? This should be 1. So the value of the program counter will be loaded when program counter write signal is active. Or the end of this to signal the 0 and program write control signal are 1. The fourth step for the archetype option is the completion step. And for the load down a store, memory is memory access step. As you can see in the archived instruction, the OILU output should be stored back in the register file that is determined by instruction register field 11 1815 or the putting the load and a stored memory. In the fourth step and load instruction, we have to read the memory index by ILU output and save it into memory data register. The store bought the memory that is addressed by all output should be not the path for the load in instruction or word. We will use the ILO output as the address. So this signal I or the it should be 1 because we want to use our value output as the address of the memory. Also memory read signal should be 1. This is memory it. This should be 1. And we write should be 0, of course. And then this data will be read from the memory, and we will store it into the memory data register. Memory data register has no control signal. So to always load by the data that we have here every cycle. But an instruction register has the right control to control it when we want to store something from memory inside it. Only in the second step, actually we active this one. And the other part it will be the active. So this instruction will be fixed during the execution part. So these are big data part for load for a store. Again they are do out will be used as the address. So this I or the should be 1 and all U out will be used as the office of the memory. But this time the value of the be registered should be stored or used as the right data. And finally, for the R-type completion, the result of the IU should be come back and store back into the register file. So this multiple extra or memory to register should be 0 because we want to select this one. So this is the right data and this multiple Excel register destination should be 1 because we want to use this field of the instruction or the instruction 1115 as the register number to store it and store this value inside it. And the last step or 15 step is for load word instruction. In this step, the memory data register will be stored back inside the register file that is indicated by value of instruction register 16 to 20. So in instruction, register 16 to 20 will be used as the destination register. So this register destination should be 0. And here the data memory register will be selected and it will be used as the data that we want to store in this register. So write data comes from this part and the number of the registers that we want to store this number inside, it comes from instruction 16 to 20. Let's investigate how multi-cycle works for a particular instruction at a time. We will start with our format. Assume that we want to execute this instruction. Add an instruction $A0 is the target is 1 and storage stores are 2 operand. If you want to convert it into the machine code, this will be the opcode 6.0 for all of the type the RC is this value or T and RB. According to the numbers of this 3 register, we don't have any shift amount in this instruction. And the function for AD is 1 and 50. In the first cycle of our format, we have to perform the instruction, fetch and update the program content. So this is the fixed step for all of the instructions. We can see the program pointer will be used as the address and the value of the memory will be stored in the instruction register. Also the program counter and 4 will be selected and given to the value and the result will become back and stored in the program content. So these are the necessary signals for the first step or first cycle of the ART type for our format instruction. In the second step, we have to read the operand from the register file and save them into the temporal register and B also for the immediate instruction or typing instruction. We have to compute the immediate value and it can be first performed sign extension and convert it into the 32 bits. And this 32 bits are here if we have for example add immediate, but here in this example we have simple add. So we only use to select this input of the audio source B. So as you can see in the third cycle of the ART format, we select our source A equals 1 and only source B equals 0. Or these two inputs are selected, they are given to the value. And also the function part, which is at 100,000 is given to the oil you control and oil you control. Perform this addition and the result will be inside oil you outrageous. And in the fourth cycle the new result will become back this multiplex. There should be 3 select input 0 and this multiple Excel should select input 1 which is the destination is 1 or just the write is 1. Memory to register is 0. So this is which is the destination? It is 1. This is memory. To register, it should be 0. By this way, the result will be a store in the register file that is indicated by bit 11 till 15 of the instruction. This part. So these are 4 cycles for our tidiness action. Let's take a branch equality instruction. This instruction requires 3 cycles. Assume that you want to execute this instruction branch equal sign as 0s1 and the label L1. If they are equal, we want to jump to this target label. So the label indicated by the 6 bits. And these are the Rs and RT. And upward of this branch record is 000100. So the first step is the same as all of the instruction. Switch the instruction and update the program counter by 4. In the second step, we have to compute the target address. So the program counter comes here from this part and the sign extended shift 2 times to the left with the selected from this part and these two value will be given to the value. So we compute the target address and store it in the value out. Also, meanwhile, the value of the first and second operand in this example is 1 and as 0 will be read. And a store in the just A and B, but for now the value output is equal to the target label. In the third step, according to the 0 flag of the value, which indicates that A and B are equal or not, we will decide to load the program counter with this target address or not. So the value operation should be 0, 1 because we want to subtract these two values. Then this 0 flag should become to this end and the PC write control should be also 1. If both of them are 1, then the program counter load will be activated and the value here will be load inside the program counter. But if the 0 flag is 0, it means that the R and B are not equal. So we don't want to jump. This is the way that the branch instruction will be executed.